All right, this lecture is on factors that influence power. Let me just return and review the last few slides from the last lecture, and that is, when the null is false, the probability of rejecting is the area under the second distribution, that's part of the rejection region. What that means is, if this is the distribution that's described in our null hypothesis, because if we describe a mean through the three amazing facts, we know this distribution is normal around that particular mean. Now, if we set our rejection region here, this is 0.05, then any means that are less than this brown line would be rejected. Any means that are greater than this brown line we would fail to reject. So these are the means that we fail to I'm sorry, these are the means that in which we would reject the null hypothesis. So we reject, and if the null hypothesis is not true, then we fail to reject all of these means, which produce a probability that we call power. The probability of rejecting a false null hypothesis is power. This is beta, this is the error, this is the probability of a type 2 error. Here's the probability of a type 1 error and the probability of a correct decision. Okay, so we want to increase as much power. We want to have as much power as we can. So, excuse me, we have to have a conversation about factors that are going to influence power. The first is alpha. If we increase alpha, that means we move this brown line over and over and over and over, we will increase power. This purple area becomes bigger as we move our brown line to the right. However, we don't want to do that because it would increase alpha. All right, and that is the probability of a type 1 error. So we don't want to change power by changing alpha. We want to do something else. But it is the case that changing alpha does change power. One of the big determiners of power is variability, and that is that we know the spread of the distribution. If we shrink the spread of the distribution, we will increase power. And what you can see here is the purple area relative to the complete distribution is gotten larger as the distribution has been squished together. The spread of it is not so great. Sample size is an enormous determiner of power as well, and that is because we're changing the standard deviation of the sampling distribution by changing what's in the denominator here. As we increase n, we decrease this, thereby again squishing this distribution, squishing the variability, the spread of it, lessening the variability, making it a thinner sort of distribution. That makes this area much larger relative to this area over here. Another factor is effect size, and we think of effect size as the difference between the central tendencies or the centers of these two different distributions. The further we push them apart, you can see that alpha is set here by the first distribution, not by the second, but as we push these apart, power becomes bigger and bigger and bigger. So, just to review, alpha, or significance level, is a factor that influences power. Other ones that I didn't talk about or didn't demonstrate, but you can see in the book, we have figures that try to illustrate these. Parametric statistical tests are generally more powerful. Variability. Decreasing variability will increase power. We can measure more accurately, you can design a better experiment, you can standardize procedures for acquiring data, you can use a dependent sample. Remember when I introduced dependent sample T, I suggested that you should always try to design your experiments that way. It's because you gain enormous power through a decrease in variability. A directional alternative is more powerful than a non-directional alternative, and increasing sample size is the other way. And this is the most commonly used way to increase power, and that is to increase sample size. And you can see what I've tried to illustrate here is as you increase the n, even though the standard deviation of the population stays the same, the standard error of the mean decreases, but it comes at some cost, and that is that if you multiply your sample size by 4, you only get a half, you only get a 50% reduction in your variability. So it's very costly to reduce variability this way, but it may be the only way that you can do it. This shows you 3 normal distributions, each with the same mean, but with different standard errors of the mean. And you can see this blue distribution has a lot of spread. This pink distribution has less. This green distribution has less. These are normal distributions with standard deviations of 2, 1, and 0.5. If your critical value was down over here, you can see that it would be really likely to reject if the situation was the green, but not if it was a blue, and so on and so forth. So hopefully this figure shows you a little bit about the implication of increasing sample size. All right, we'll talk to you soon.